Hey guys, welcome back. We're going to be moving on to our next chapter, chapter 18, confidence intervals for proportions. We'll be talking about sea fans in the Yucatan Peninsula, specifically the Las Redes Reefs, which is down by the Gulf of Mexico, and also part of it is in the Caribbean as well. So researchers are studying aspergillosis. I have no idea how to pronounce that. I did my best. But anyway, it's a disease that infects sea fans and that are living in the coral reefs. So you can kind of see the before and the after here. So obviously it's really bad, and we don't want this disease to spread. So they want to see what is the extent of the damage, or what proportion of all sea fans in this area or this region are infected by aspergillosis. So the true population, which is going to be the percentage at any given time of the sea fans that are infected, that proportion that exists, it's real. That's a real proportion. Maybe it's 50%, maybe it's 46%. We don't know. There is a total number of sea fans out there, and there is a certain percent of them that are infected. The problem is that's a number that we can't really know, and it's always changing, right? So it's kind of one of those things, like the number exists, kind of like the number of hairs on your head, but nobody really knows how many hairs are on your head, and it's constantly changing, right? So the true proportion is a real number. It's just a number that literally only God knows. We don't know. But the best we can do is to take a sample, and then from that sample try to create some sort of a confidence interval to be able to estimate what range of values we think that true proportion is going to be in. And that's where inferential statistics comes in. So this is really answering a question that we use statistics a lot for inference, to be able to estimate what we think the extent of the damage is. So I think you guys will enjoy this. So they sampled 104 sea fans, kind of randomly selected, not all doing it from the same area, because they're probably not going to be independent, because it might be contagious. Like, the disease might be more likely an impact. If it's really bad in one area, it might be spreading from that area. So they randomly sampled from all over the region. But the other problem is that they're so far down, they couldn't get a really large sample size, because they have to dive to all the locations and then sample part of it, take it back up, and then run lab tests on stuff like that. So of the 104 sea fans that they randomly sampled, 54 were infected. So again, it's important they randomly sample. That way it's a representative sample of all the sea fans in the region, not just the ones that are easy to get to and convenient and stuff like that for us to go get. Okay, so 54 out of 104 is a sample proportion of 51.9%. So from our sample, we believe, it's like the small amount, we believe that 51.9% of all of them are infected. Now, the true proportion, which would be like all the possible M&Ms, right? This is like all the possible sea fans that are out there. That true proportion, surely it's not going to be exactly our sample proportion of 51.9, but it should be close, right? And how close depends on how large our sample is. And as long as we don't have any outside sources of variation, or make sure that's independent and that our sample is actually representative, and we didn't mess up in any of the other ways we could have gathered our data. So what can we say from that? Well, our sample proportion is 51.9%, right? We know that because that's 54 out of 104. The true proportion of sea fans, again, that's literally one of God only knows things, like the number of hairs on your head. Okay, we don't know that. Okay. That's what we're trying to estimate, though. And so what we do is we create our sampling model. Now, the sampling model is actually going to be centered at the true proportion. So the sample that we got was just one sample out of all the possible ones. Like when we're flipping the coins, we know the true proportion should be 50-50, right? And so then, depending on the number of our sample size, we can create a standard deviation in our sampling distribution model, like what we have here. And so the question is, what was our sample? Well, we would expect 95% of samples to be within 2 standard deviations on the sampling distribution model, right? And so, but we don't know where this one sample, where it landed there. And if we took another sample, it would be different, right? Maybe that one would be less than 50%. We don't really know, right? So what's going to be the spread for this? Well, normally the spread for a sampling distribution model is found by doing a p times q divided by n, but we don't know what p is. We don't know what q is. So instead we use the next best thing that we have, which is p hat from our sample. So we would do 0.519 times 0.481, which would be q, and then divided by our sample size of 104, and then that'll give us our standard error. Now, we call this a standard error because it comes from our sample, and we know it's not actually correct, right? We know the true proportion. It'd be very rare for our true proportion to be, it's like flipping exactly 50 heads, right? We're not going to expect that out of 100, right? So we know it's going to be off, but it's our best estimate because it's the best sample that we have at that point. All right, so what do? We know it's going to be kind of close to the sample proportion, but we have to create a range of values to be able to capture it. So we call that our confidence interval, which is when we take our sample proportion and we add and subtract to it some margin of error. And what we're going to do is we're going to go 2 standard deviations in both directions, and then 95% of the time we would expect our sample to be within 2 standard deviations of the sampling distribution model of the true proportion. And so therefore, if we go 2 standard deviations out from our sample proportion, we would successfully capture the true proportion 95% of the time. Okay, so that's where we get 95% confidence intervals. We go from our sample proportion, whatever that was centered at, which for us was like 52 or 51.9, basically 52%. We go 2 standard deviations in both directions, adding and subtracting that margin of error in both ways, and then that'll be our 90% or 95% confidence interval. All right, so let me try to model this out for you. So here's our true proportion, whatever that value is. Again, the God only knows value. And then from there, we go 2 standard deviations over. We would expect 95% of our samples of 104 C fans. And if we went out and we gathered another sample of 104 C fans, it would vary, and then it would vary again, and it's going to vary all over the place, okay? But 95% of the time, it'll be within 2 standard deviations, roughly. So that's our sampling distribution model. But again, it's based on the proportion we don't know and the standard deviation that we don't know either, because the standard deviation is based on the proportion. All right, but what we do have is this 51.9%, which is from our sample proportion. Now, we don't know where it's landing from the proportion, but 68% of the time it'll be within 1 standard deviation, 95% of the time it'll be within 2 standard deviations. So from our sample proportion, we build this 95% confidence interval where we go over 2 standard deviations, and this would be our right bound and our left bound, and notice it would successfully capture the true proportion 95% of the time. So if our proportion was varying more than 2 standard deviations from the sample, from the true proportion, then our confidence interval would barely miss and not actually successfully capture the true proportion. So that's what we're trying to do here. So, and if same thing on the other side, if it was more than 2 standard deviations, which can happen like 3% of the time or 2.5% of the time, then our margin of error wouldn't be going over far enough to actually successfully capture the true proportion. Okay, so our confidence interval is going to be our proportion, which is from our sample, the p hat, plus or minus our margin of error, which our margin of error is just going to be 2 standard deviations if we're doing 95% confidence. We'll get into more critical values and stuff like that tomorrow, but that'll be a lesson for another day. So each one of those we said was 0.049, roughly 5%, so about 10%. Adding, subtracting that from this will give us 2 different ways that we can summarize or state the confidence interval. You can write an interval notation, which is basically like an ordered pair, but we have our left bound and our right bound. So all right, so in our interval notation, if we are writing it with these parentheses, then we're saying it doesn't include the left bounds like the far end, so it's strictly greater than 42.1% and strictly less than 51.9%. So just a small little correction that I had to make there. All right, so the population is the entire group of individuals being examined. It's also called a population of interest, and what we're examining is called a population parameter. So for instance, we're interested in all the sea fans in the Losaritis Reef, and the population of parameter that we're interested in is the proportion of them that are infected by aspergillosis, or however you say that. The sample is going to be the group of individuals that we selected to represent the population, which was 104 sea fans. The summary statistic we get from it is called the sample statistic, which in this case would be our sample proportion. So whatever proportion we got, which was the 54 out of 104, and then the total proportion is going to be whatever that value is that we're trying to estimate in this case. So a few of our conditions must have a random sample condition. Representative samples come from random samples, and so if it's not randomized, that's when bias comes into play and lurking variables and stuff like that. So we have to randomize our sampling, otherwise we can't expect our sample to be representative. And if we say the sample is representative when the sample statistics accurately reflect the population parameters, which is the whole point. We're trying to estimate the true value of P. So we need to make sure we follow all of our other statistical practices of gathering data to make sure we get a good representative sample. Next thing is independence. So we have to assume they're independent, but if we're sampling without replacement, once we sample one reef, we're not going to sample another CFAN or whatever, the same CFAN twice. And so we are sampling without replacement, but as long as we're sampling less than 10% of all the CFANs in the area, of the population or whatever, then we're fine. We can override the independence assumption with the 10% condition. So that's important because technically once we've removed one of them, like removing an ACE, it's sampling without replacement. Probability of getting another ACE is going to be different. So we still must make sure we are expecting at least 10 successes and 10 failures. For us, with a sample size of 104, we had 54 successes, and so that were infected. So we clearly had enough, more than 10. If not, it's going to be cut off by hard left bound of 0 or hard right bound of n. So statistical inference is using data from a sample to make conclusions or inferences about the population. The first step in statistical inference is to create confidence intervals, which we just did. We gather data from a sample. Hopefully our sample is representative of the population. We hope the sample proportion p hat represents the population proportion p, so that we center our confidence interval at the sample proportion. But our sample isn't perfect, so we create a interval with a margin of error. Let me actually go ahead and show you how we would put that in the calculator, by the way, because it will create confidence intervals for you. So we're going to go to stat, arrow to the right to calculate now, or to test. We haven't done tests before. This is the first one, right? Because so arrow, there's a lot of different tests. We're going to be going over all these in the next like 2 months, so it's pretty exciting. We want to do a 1 proportion z interval. It's a z interval because it's based off of a bell curve. We're dealing with proportions. We can approximate that with bell curves instead of a T model. So X was the number infected. We had 54 infected out of 104. And then just select the level of confidence you want, which we're going to do 95%. Hit calculate, and it'll give you those values. So it'll do all the, there's your interval notation. So they do use parentheses, so they're strictly larger than 42 point that and strictly less than that value. Okay, cool. They'll also tell you the p hat sample. They'll do that math for you and the overall sample size there. Okay, cool. Standard error. So the sampling distribution model is centered at the true value of P, and the standard deviation of that is calculated from P and Q, like when we knew it was 50% for a fair coin. But it's rare that we ever actually know what those values are. Normally we're trying to predict them, so that's where the standard error comes into play. Standard deviation is based on the true values of P and Q, which we don't know. Again, it's one of those God only knows things. So it's centered at P with a standard deviation of that. But our sample, the next best thing we have is based on the standard error, where we use P hat and Q hat, which come from our sample, which is the best estimate that we have up to that point. Unless we took a larger sample, then we'd have a better estimate. But anyway, so we call that a margin of error because we know it's not going to be exactly the same, but it should be hopefully close enough that it's not going to throw off our model too much. So that's just why it's called margin of error. All right, a sea-level confidence interval or model parameter is an interval of values usually in the form found of data such that C% or 95% in other words or whatever, or 90% or 99% of all random samples will yield intervals that capture the true parameter value. So basically we take our estimate, like our p hat, plus or minus some margin of error, and we'll get critical values for that one tomorrow for our margin of error, so don't worry about that. You don't need to know that for today. So what can we really say about our population parameter P from our confidence interval? Well, here are a few things that we'd like to be able to say in order from the strongest to the weakest, and the reasons why we can't say them. So these are really good. I'm going to read them to you. Number one, so we would love to be able to say that we know 51.9% of all sea fans in the Las Vegas reefs are infected. So that would be nice, but that was our sample proportion, and we're pretty certain that that's not going to be what the true number is. And besides that, this true number is changing all the time. And we'd be really, really lucky if it was exactly that, right? So it would be nice to be able to make absolute statements about population values with certainty, but we just don't have enough information to be able to do that unless we could take a census. But that's out of the question. There's no way to be sure that the population proportion is the same as the population sample proportion. Sorry. In fact, it almost certainly isn't. Observations vary. Another sample would yield a different sample proportion. So if we did do a second sample of 104, we should actually just add those two together, and then now we have a larger sample of 208, which would be able to decrease our standard deviation with the law of diminishing returns, and then we'd have a better estimate of our P and a tighter confidence interval, by the way. All right, the second statement we like to be able to say, but it's not true. It is probably true that 51.9% of all sea fans in Las Orejas Reef are infected. So no, in fact, we can be pretty sure that whatever the true proportion, it's not going to be exactly 51.9000%. So the statement is actually not true. The problem is that we know, like for instance, is anyone exactly 6 feet tall, like to the precision of 6 feet .00000? No one's going to be exactly, or if you were, you were at some point in time. Like I'm 6'2", so at some point in my life, I had to have been exactly 6 foot tall, but I was still growing, and so I was exactly 6 feet tall for like 1 second before I was slightly taller than 6 feet, if that makes sense. So it happened, but it was very rare. So whenever you're talking about continuous random variables or a continuous distribution like the normal distribution, you really have to look at a range of values to be able to calculate the probability or the area, and that's why we use a CDF. Anyway, number 3, we don't know exactly what proportion of sea fans in Las Orejas Reef are infected, but we know it's within the interval that is between our confidence interval. That's not true, because 5% of the time it would be outside of those two standard deviations, right? And so 5% of the times we could have just had a really unlucky sample, which would be totally normal. It would happen. So really, 5% of the time we wouldn't have successfully captured the true proportion. So we're getting closer, but we still can't be certain. We can't know for sure that the true proportion is in this interval or any particular interval. Number 4, we don't know exactly what proportion of sea fans in Las Orejas Reef are infected, but the interval from blank to blank probably contains the true proportion. So that's getting better, but probably means like more than likely, and that's true because it's more than 50%, but we need to be a little bit careful. So first, we gave the interval. I guess we messed up twice. And second, by admitting that we only think it probably contains the true value, and this statement is actually true. So we're not able to say as much as we want to, but this is actually getting better. So number 5, we're 95% confident that between 42.1 and 61.7% of the Las Orejas Reef fans are infected. Statements like this is called a confidence interval, and it's the best that we can do. And that's actually true. So that's how we would state it. We're 95% confident that our confidence interval based on our sample would successfully capture the true proportion. So 95% of the samples would be within 2 standard deviations of the sampling of the actual true proportion on the sampling distribution model. Okay, so simulate this process, which is actually going to be a lot of fun. So get out your calculator here, and we're going to go to apps and then probability simulation, and then toss coins, and then go into your settings, and then advanced settings, which is the window here, and we can actually change the weight to these probabilities. So let's imagine that we actually have privy information and we know the true number of sea fans that are infected. So I'm going to change mine to 42%. So 42% of all sea fans are infected, and I'm going to click OK. I'm going to go ahead and write that down before I forget. Okay, so the true proportion is equal to 42%. Now we're going to create a random sample of 104, and then create a confidence interval to be able to try to estimate this value, which is 0.42%. Okay, so now trial settings, I'm going to change that to 100, 104, just so we match what we did from the book. Click OK, and then yes, and then toss. So how many heads did I get? I got 54. So well, that's kind of cool. That's exactly the same thing they got. Okay, yeah, sure. So my sample was 54 out of 104, which is approximately, I don't know, I got to quit out of this now. So escape, yes, quit, yes. All right, so 54 divided by 104, which is going to be the same thing we got before, which is 0.519. Okay, so I'm going to create my confidence interval and see if I successfully captured the 42%. So I'm going to go to stat, test, and so you actually haven't seen these before. So stat, arrow over to calculates, one variable stats, all the stuff that we're used to, right? Now test is going to be all the stuff for inference, and we're going to actually figure out what all these are before in 2 months. So yeah, it's going to be pretty great. So we're going to do a one proportion z interval. One proportion z interval, which is alpha. Okay, cool. And I'm going to say that we had 54 out of 104 and want 95% confidence, which is between 42 and 32. Ooh, very nice. Let me see. I can actually click and drag that, I believe. Yeah, there we go. How cool. Didn't mean to do that. There we go. Okay, so that's my confidence interval for 95% confident. Now the true proportion was 42%. So look what happened. We actually failed to successfully capture 42%. So this can happen. It was very rare. I'm glad it happened here. So our true proportion was 42%. Our sample proportion was 51. Let me lock this in place. It was apparently right outside of 2 standard deviations above it, which is interesting. Which means that we did not successfully capture. 95% of the time we would have successfully captured the true proportion, but this is one of those 5% of the time that we didn't. So interesting. Yeah, you got to be careful. But that's what we do for confidence intervals. So we would conclude 95% of the time, we are 95% confident that between 42.3% and 61.5% of all of our samples would capture the true population proportion. All right, number 2, margin of error. A medical researcher estimates the percentage of children exposed to lead-based paint, adding that he believes the estimate has a margin of error of 3%. Explain what the margin of error means. So that means that he is some level of confidence sure that the true proportion is within 3% of his sample proportion. So he believes the true proportion is within 3% of his estimate, which his estimate comes from some sample, some survey or whatever. With some probably 95% degree of certainty. 95%, like the 2 standard deviations we did, that's pretty standard. It's kind of like the default. Number 4, consider each situation described. Identify the population in the sample. Explain what P and P hat represent, and tell whether the methods of this chapter can be used to create a confidence interval. So a consumer group hoping to assess customer experiences with auto dealers surveys 167 people who recently bought new cars. 3% of them expressed dissatisfaction with a salesperson. Nice. All right, so the population of interest is going to be all people who go to an auto dealership, so who go to a car dealership. Now the sample is just going to be 167 people who actually bought the cars. They probably are not just interested in people who bought cars, but the people who dealt with the salesman at all. So the people that didn't buy a car, those are still people we need to talk to. So this is not a very good sample. The sampling frame is not matched up with the people who actually had an experience with the salesman. So if people were really dissatisfied with the salesman, they walk out and they wouldn't have bought a car. So you kind of have that issue, right? The P is going to be the true proportion of people who were dissatisfied, true proportion of people who went to the dealership that were dissatisfied with the salesperson. The P hat was our 3% that expressed dissatisfaction with a salesperson from our sample. So can we create a confidence interval? Is it plausible independence? So each person that comes in, are they independent of the next person? I suppose as long as they're not related. They are dealing with the same salesperson, so I mean it's probably important that we do a random sample. We're not just taking all the people from one day, from one shift, or from one salesperson. So they didn't. Did they say it was a random sample? They didn't. So I'm hoping that they did a random sample, so that we can avoid a lot of those issues, and that it would be representative, that the sample of 167 people is representative. But also we would have issues because they didn't survey people who didn't buy cars, only those that bought the cars. 10%, certainly this is less than 10% of all the people. If it's just one dealership, was this over a year, was this within a month? So we might have had too large of a sample that we would have issues, so we would have to be careful. So we're assuming that there's more than, that they sell more than 1,600 or 1,700 cars in a year or whenever they did the survey. Success failure, 3% of that value, well, let me put it in the calculator real quick. So 0.03 times 167 was only 5%. Okay, so only 5 people were dissatisfied, in other words. So our success failure condition was not satisfied. So it would not be appropriate for us to use a normal model, which is what all of our statistical inference is based on. So our sample wasn't large enough. If we found a sample of 3%, we would have to do 10 divided by 0.03. We would have to have a sample size of roughly 333 people in order to be able to satisfy the success failure condition. Part B, what percent of college students have cell phones? That many students were asked as they entered a football stadium. 243 said they had phones with them. All right, so the population is going to be college students, but our sample only came from students from one college, so that's a problem. The population of interest, if we're only interested in that college, then we're fine. Also, this is a convenient sample, right? So people who go to the games might be more likely or less likely to have phones. So this is not really a good way to do it. Convenient samples are never a good way of doing it. You're not randomly selecting anything. It wasn't randomly sampled, so we have issues with that. Our p hat is going to be that divided by that, whatever that number is. The true proportion is going to be the true proportion of college students that have phones, cell phones. 10% condition, this is certainly the sample that we did is certainly less than 10% of all the college students as long as there's more than 28,000 college students. I suppose that could be an issue if it's a small college. We had more than 10 successes and more than 10 failures, so that part's okay. The real issue is how they gather the data, and if they're trying to draw conclusions about all college students or just college students from that college. So, all right, confidence intervals, number 7. Several factors are involved in the creation of a confidence interval. Among them are sample size, level of confidence, and the margin of error. Which statements are true? So for a given sample size, a higher confidence means a smaller margin of error. So if we want to have a higher confidence, we have to go more than 2 standard deviations, right? So if we went 3 standard deviations out, we'd have more confidence, but it also means a larger margin of error. So that's going to be false. That's actually backwards. For a specified confidence level, larger samples provide smaller margins of error. Yes, as we increase the sample size, the margin of error is going to shrink. So that one is true. Okay. For a fixed margin of error, larger samples provide greater confidence. So if we have the same margin of error, yes, a larger sample would allow us to increase our confidence level if we fix the margin of error. So yeah, that's true. Basically, the formula would be the margin of error is equal to some critical value times p hat times q hat divided by n and the square root of all that. So if you're increasing your sample size, it's going to either decrease the confidence interval or it's going to increase your margin of error. So essentially, those two are indirectly related. These two are directly related because it's multiplication. For a given confidence level, having the margin of error requires a sample size is twice as large. It's actually 4 times as large. We talked about that yesterday. So that one's not true because it's the square root of 1 over n, and the square root of 1/4 is equal to 1/2. Okay. All right, so that's it. If you have any questions, please let me know. We'll stay on this chapter for, I think, 3 more days, so to kind of give ourselves some time to go deeper into soak in. So let me know if you have any questions, and if not, I'll talk to you guys later. Hopefully, I'll see you guys in class sometime if the snowmageddon never ends.